So I'm going to state and prove the Kaplansky's density theorem. And let's just fix some notation. First of all, whenever I have some subset B of H, when I talk of the closure of B, that will be the strong operator topology closure, but actually it will be a it will be a convex subset all the time, so we actually know that that's the same as the weak operator topology closure of B. So I will not distinguish between S and W when I write this up, in order to not drown you in notation, but as you'll see in the proof, it's very important that we keep track of which topology we're using, because we need to sort of jump back and forth between the two choices of topologies to work with. We'll also say B1 will just be the intersection of B with the unit ball of B of H. So that's just the T's B of H, norm less than 1. We will talk of BSA. That's the intersection of B with the self-adjoint elements in B of H. So you know what that is, but let me just write it out. Where T is T star. And also B plus will be the intersection of B with the positive elements of B of H. And these are sort of standard things that we've talked about several times. But the point is that these conditions here that I'm working with, they are tricky to work with together with the strong and the weak operator topology, because there's a lack of continuity of the norm and of taking adjoints with these weak topologies that we need to somehow address. So this is the theme of Kaplansky's density theorem. So I'll just state the theorem. It sort of comes in 4 statements. 1, 2, 3, and 4. And so the first one is that when I take the closure of the self-adjoint part of A, that is the same as the self-adjoint part of the closure. When I take the closure of the self-adjoint part with the units of the unit ball, I get the same as if I close off A and then take SA and 1. If I take the same with the positive elements, get the statement plus 1. And finally, if I take the closure of the unit ball, that is the same as the unit ball of the closure. So this is when A is a C star subalgebra of B of H, same unit as usual. So, I mean, when you look at the statement of Kaplansky's density theorem, it doesn't look very impressive. It just sort of tells you that it doesn't matter in which order you pass to self-adjoints or norm 1 or positives compared to when you close off, right? So the closure of the self-adjoints is the self-adjoints of the closure. The closure of the norm 1 self-adjoints is the norm 1 self-adjoints of the closure, etc. And it's mainly number 4 which is useful. And I mean, in this course, you're not really going to see the importance of the Kaplansky's density theorem, but if you're moving on to anything in this direction, it's going to pop up because it's one of the most important results in practice in operator algebra theory. So so this is really sort of the opposite from what we've seen in many cases. The statement of this theorem is not very appealing, and the proof is hard, but you'll see along the way many of the methods that we've developed in the course will be used in a non-trivial way. So I think it's worth doing it, even though we're not going to see the consequences of Kaplansky's density theorem a lot in this course. Okay, so my plan is to prove this result in its entirety in this pencast, except for one fact that I'm postponing to the next pencast. So I'll point it out when I reach it. But otherwise, I'll follow my principle of greedy pencasts. So I'll just do whatever is easy first. And in fact, my first claim is that the inclusion from left to right is easy to see in all of the 4 cases. So this is true simply because this follows by the observation, maybe observations, that B of H, SA, and B of H plus and B of H1 are closed in strong or weak operator topology. It doesn't matter which one I'm using because I'm talking about some convex sets. And why is that? So B of H1 is closed since it is compact. This is the Banach-Alaoglu result. And for the self-adjoints, we can maybe write it like this. So it will be the intersection for all x and y's of all the t's in B of H, where the inner product of tx with y is real. Right? So we have a criterion for checking whether or not an operator is self-adjoint. We can do this by computing all these inner products, txy. Oops, sorry, I don't mean txy, I mean txx. Sorry, like this. Oops. Like this. And these sets are clearly closed in the weak operator topology because they're pre-images of, I mean, I'm looking at the map that sends T to the inner product of Tx x. This is one of the functionals that we're using to define the weak operator topology. And then we're taking the pre-image for every x, we're taking a pre-image of R, which is a closed set in C, of this map, and then we're intersecting all these closed sets, right? So this is these sets will be weakly closed, so the intersection is weakly closed, and hence so is B of H SA. And so this is a characterization we've done before, which is now handy, and I can just do the same with positivity. That's just saying that Txx is contained in the positive half-axis. So it's the same argument I'm using in both sides, using this key observation. So this means that the three sets that I've introduced, they are all closed in the topologies that we're looking at, and so since I know that the self-adjoint in A lies inside the intersection of the closure of A and the self-adjoints, then because the closure is the smallest closed set containing, I get the inclusions. Right. So this is all clear, and the interesting observation here is that none of the other implications that we need to establish are going to be clear. So this is really, there's hard work in each of them. Okay, so let's get going. So now I'll do the first one. So what I'm going to note is that the map T goes to T star is in fact what continuous, not sot. Sorry, right? But we've seen that taking adjoints is not a strong operator continuous map, but at least it is weak to weak continuous, right? And since this is the key for my argument, let me just point out why. I think we've had this before, but what does it mean that T alpha goes to T in the weak operator topology? It means that for all x and y's, the inner product of T minus T alpha applied to x and y goes to 0. But now I can take stars, right? So that will be x and then T minus T alpha star on y goes to 0, and that's the same as saying for all y and x. If I just change the sides of the vectors, which will cost me a complex conjugation, but that will still go to 0, I know that T star minus T alpha star applied to y, x goes to 0, and that's exactly the same as saying that T alpha star goes to T star. Right. So I know that T maps to T star is what continuous. So consequently, the map real part of T divided as the average of T and T star is also weakly continuous, because we also know that multiplying by a scalar and adding is weakly continuous. So now we can finish the argument in a fairly easy way, but let me do it slowly because I'm going to need to do this again several times. So we fix something that lies in the right hand side of the set equality. So this is in the self-adjoint part of the closure of A. Right. So now I will fix some net T alpha, which comes from A, and I know then that T alpha goes weakly to T. Right, so I'm using here that we have the right, I'm choosing to work with the weak operator topology. I have a choice because my set working with is convex, so it doesn't matter. But you see it's very important for the proof because I actually do not know that taking the real part is strongly continuous. So that's important. Okay, so since I know this, we conclude that if I take the real part of T alpha, this will converge to the real part of T, right? But the real part of T is just the average of T and T, because T by assumption is self-adjoint, right? So this is just T. So the real part of T alpha also converges to T, and that's what we need, right? So T is in the closure of the self-adjoints of A because I've demonstrated some self-adjoint elements, the self-adjoint by construction, that converge to T. Right. So this is really the kind of argument that you'll see twice more in order to establish number 2 and number 3, is that I can make some sort of operation on the elements that are approximating T, so that they are. I can make a new approximating net which has the same properties of T, and for this I need some sort of continuity, and that's exactly how that's going to go. So note that by 1 we may reformulate 2 and 3 a bit to, let's say, 2' and 3'. So I can make this slightly easier for myself, because I will just say that what I need to prove is that the norm 1 self-adjoints is the same, the closure of the norm 1 self-adjoints is the same as the closure of the self-adjoints unit ball, and also the same with plus. So I'll do it like this, plus comma 1. Right, so I mean, in the original, let me change color here. In the original statement I had that this was supposed to be the same as A closure SA1. Right, so I'm taking the intersection both with the self-adjoints and the norm 1 elements. But by 1 we know that this is the same as ASA closure 1. Right, so this means that in all that I'm going to do from now on, I can work exclusively with the self-adjoint elements, and that makes it slightly easier for me. So so really what I need to prove is to find the inclusions in 2' and 3' from right to left. So, and here is now the key part of the argument that I will not prove here. It will come in the next pencast. It is a fairly long proof in itself, sort of a Stone-Weierstrass type of argument, and it simply says that when f from R to C is continuous and bounded, then the map sending T to f of T is strongly continuous on B of H SA. So what I'm doing here is I'm saying I have my functional calculus, I can apply it to self-adjoint elements, and I will apply it using some function called f. I will assume that f is continuous and bounded, and then the statement in the lemma is that the procedure of taking t and replacing it by f of t is going to be strongly continuous. Right? So if t alpha goes to t, all of them being self-adjoint, then f of t alpha will go to f of t. So this is the idea, and I'll, as I said before, I will prove it on the next pencast. So how are we going to use this to prove the inclusions that I need to establish for 2' and 3'? Well, I'm going to do it this way. So it's going to follow the argument that I just gave you in number 1. So I will define a function called f2. I will define it to be -1 when t is less than -1. Let it be t if t is between 1 minus 1 and 1, and I'll let it be 1 if t is bigger than 1. So f2 and f3 that I'm defining in a second will be defined on the real axis. And f3 of t is somewhat similar. It's 0 when t is negative. It's t when t is between 0 and 1, and it's 1 if t is positive. So let me just sketch the graphs of these two functions. So here's minus 1, here's plus 1. So the one here has this graph here. So it's never bigger than 1. It's never smaller than minus 1, but it is the identity on the interval from minus 1 to 1. And the other one, think of a reasonable color here, green, looks like this. So it is 0 here, and then it follows the other function that I just showed you. Right, so the point is that I'm going to apply these functions to my operators using the functional calculus, and as we can see, if you plug in a self-adjoint element in F2, you'll get a self-adjoint element which has norm less than 1, because the function that we're using is bounded in the uniform norm by 1. And if you do the same with the green function, you'll even get a function which is positive, right? But of course, you're changing the element this way, so in order for us to reach the conclusion, we have to be a little bit careful, right? So let's prove the one for 2 prime, right? So what is it I know? So we fix some t, which is in the closure of the self-adjoint elements of A, and also has norm 1. Right? Then we take some t alpha, which is in the self-adjoint elements of A, so that t alpha goes to t. This time it's essential for me to use the strong operator topology. Doesn't matter except in the proof, right? So now I have taken t alphas. What's wrong with these t alphas? I don't know they have norm 1, right? So I don't know that t is in the closure of the self-adjoint elements with norm 1. I just know that t is in the closure of the self-adjoint elements and that it has norm 1, right? But now we get from the observation before that if we apply function 2 to t alpha, this converges strongly to f2 of t. And the point is that t is a norm 1 self-adjoint operator. So that it means that its spectrum lies in this part of the function, of the real axis, right? And on this part of the real axis, the blue function, which is the one that I'm calling f2, is the identity. So when I apply it to t, nothing happens. Right? So the f2 t alphas will converge strongly to t, and that's exactly what I need, because the f2 t alphas, they lie in the self-adjoint elements of A with norm 1, right? Because they were self-adjoint all the time, but now they've also become norm 1 because I'm applying t alpha to it. And then you can sort of see that the same argument for 3, it works in the same way. I take t alpha going strongly to t. This time t is in ASA 1 plus. So I take the t alphas going to t, they're self-adjoint, and then f3 applied to t alpha goes to f3 applied to t. And this time I know that the spectrum of t is contained in the 0, 1 element interval. So this means that ft of 3 also is t. This time I have a smaller I have a smaller interval where my function is actually the identity, but that's fine because T's spectrum lies in that interval, and so I get that this F3T alpha converges strongly to T, and then F3T alpha is in A plus 1 because it's positive, because F3 is a positive function, has norm less than 1 because the F3 has norm less than 1. So that is the end of the proof of the inclusion of at number 2 and number 3. So we're not quite done yet. We need to do number 4. And we will do this by appealing to number 2 and then use what is generally called a matrix trick. So let me explain how that works. So I fix some T, which lies in the right-hand side of the equality. So it means that it's in the unit ball of the closure of A. And then what I'm going to do is I will consider an operator that lives on 2 copies of H. So it's going to live in B of H plus H. So I will simply take a Hilbert space which is twice as big as the one that I looked at before, and try to work with that. And the point you can see is that I'm making sure that the matrix operator, which lives on the bigger Hilbert space, is self-adjoint, because T is not self-adjoint, but I will simply put things in a matrix, a 2x2 matrix, in such a way that what I'm building is self-adjoint, right? So this, maybe call it T bar, this operator T bar is self-adjoint, and its norm is bounded by 1, I claim. And why is that? Well, if we look at to compute the operator norm of T bar, we have to take, the supremum of vectors in H plus H, norm less than 1, and then I'm applying T bar to that vector. Maybe I'll rewrite this so that it looks like a vector, like this, and then I have the norm of T bar applied to xy, like this, and let me work with squares so that everything becomes a little bit nicer. So I'm computing the square of the operator norm of T bar, but as you'll see, it's 1, so also the operator norm itself is 1, or no more than 1. So what is this supremum? So it's the supremum of x squared plus y squared is less than 1, because I'm using Euclidean norm. And what happens when I apply T bar to xy? Well, I get the vector ty, t star x, right? So when I'm applying, you can just like a matrix multiplication. The first row is 0 times x plus t times y, so that gives me ty. Second row is t star x 0 times y, so that gives me t star x with a square, and then this is the same as the supremum, x squared plus y squared is less than or equal to 1, and then the norm of ty squared plus the norm of t star x squared. But I know that t has norm less than or equal to 1, and I actually also know that the t star has norm less than or equal to 1, because we know that taking stars is an isometry. So this will be less than the sup of x squared plus y squared less than or equal to 1, norm of y square, norm of x square, where what I just used was that the norm of t and the norm of t star were both less than 1. Okay, so now it's clear that this is 1. So I found a self-adjoint norm 1 operator, and we note that this then lies in, well, I mean, it sort of comes from the 2 by 2 matrices of the closure of A, right? So I sort of made it with 4 operators that go between H and H. 2 of them are 0, one is T, the other one is T star. They all come from the closure of A, and you can think of that as the closure of M2 of A, right? Because convergence in the strong operator topology we're talking about, this sort of takes place in each component of H separately. So I'm in the situation that I can apply one of the results that I've already proved, and the relevant one is number 2. So by claim number 2, we have that T bar is, well, it comes from M2A's closures self-adjoint norm 1 elements, but that's the same as the self-adjoint norm 1 elements closure. Right? So this is observation number 2, applied not to A, but to the 2 by 2 matrices over A. So it's taking place not in B of H, but in B of 2 copies of H. But then that tells us, so then there is a net T alpha bar in M2A SA1. So that T alpha bar, maybe write it like this, converges to T bar. So what is T alpha bar? Well, you know, it has sort of T alpha 1, 1, T alpha 1, 2, T alpha 2, 1, T alpha 2, 2, and this converges to 0, T star 0. So that's the same as that. So we see that T alpha 1, 2, this is strongly, and so this is strongly as well. So I've now approximated T by one of the 4 components of T alpha bar. And the reason why I'm doing that is that I claim that the norm of T alpha 1, 2 is less than or equal to 1. Right? So that's all I need. I need to be able to approximate T by elements coming from A, which are of norm less than or equal to 1. But actually, this is easy to see, because what is the norm of T alpha 1, 2 of Y for some Y line in H? Well, it's less than the norm of this whole matrix, T alpha 1, 1, T alpha 1, 2, T alpha 2, 1, T alpha 2, 2, applied to the vector 0, Y, because that is exactly the first coordinate of that vector, right? So no matter what happens on the second coordinate of this vector, it will not make the norm any smaller. And I know something about this because this is no longer than the length of 0, y 2, because I know that T alpha came from the unit ball of the self-adjoint elements of the 2 by 2 matrix over A. Right, so, and of course, that's just the same as the norm of y squared. So, hence, T alpha 1, 2 comes from A1, and we are done modulo the lemma.